Hi, today I'd like to talk about the concept of the wave function. Although quantum mechanics is extremely accurate, it's also extremely counterintuitive. So scientists has essentially resorted to a system of mathematical models to represent nature at the quantum scale. And one of these mathematical models is the concept of a wave function, which we depict as psi. Now, the wave function is basically a complex number that represents the probability amplitude of being in a certain state. So psi of x is basically the probability amplitude of being at the position x. And likewise, psi of s comma t is the probability of being at position s at time t. And so when you multiply this value by its complex conjugate depicted as psi star, you're always going to get a positive real number, and which will be the probability density. Now keep in mind that you can always find the complex conjugate of a number by switching the sign of the imaginary components. If you have a minus bi, you simply switch it to a plus bi, and that's a complex conjugate. So now to visualize the concept of a wave function, you picture basically a coordinate system where the s-axis represents the position of a particle. The second axis represents the real component of the wave function, and the third represents the imaginary component of the wave function. And so now the wave function itself is represented by a, uh, a curve that's helix and corkscrews around the s-axis. And so if you're on the s-axis, your projection to that curve will be your wave function for that position. Now, the distance that it takes for it to do a full 360 or 2 pi radians around the s-axis is what we call the wavelength, and this is a side view depicted here. Now, because the curve representing the wave function travels 2 pi radians around the s-axis for each wavelength, the angular displacement, okay, as depicted here, of the in as that the wave function traces in the complex plane is equal to 2 pi s over lambda, and the value of a complex number, in this case the wave function itself, can be written as the absolute value of the probability amplitude times e raised to I times its angular displacement. So psi of s is going to be a times e to the I 2 pi s over lambda. And that's where A is the absolute value of the probability amplitude. E to the 2 pi s times I over lambda is cosine 2 pi s over lambda plus I sine 2 pi s over lambda, which essentially, if you have e to the I theta, that's equal to cosine theta plus I sine theta. You substitute 2 pi s over lambda there, then that's equal to cosine 2 pi s over lambda, which is the real component, plus I sine 2 pi s over lambda, which is the imaginary component. Okay, also experiments showed that the momentum P is equal to h over lambda. That's where h is equal to Planck's constant, which is about 6.626 times 10 to the minus 34 kilogram meters squared per second. And lambda is a wavelength, and p is the momentum, as I stated. So now 1 over lambda is going to be equal to p over h, which we can substitute back into the equation to get psi of s is equal to a times e to the I 2 pi ps over h. Now, since h over 2 pi is usually represented as h bar, so h over 2 pi is equal to h bar, we can essentially change that equation to be psi of s is equal to a times e to the I over h bar p times s. Now, if the curve representing the wave function is moving in a positive direction with respect to the s-axis, so if it's sliding to the right, respect to the s-axis, and you're at a point on the s-axis, you're going to be moving backwards with respect to that curve. Now, with this in mind, the angular displacement of the wave function around the static point is equal to the point's linear displacement relative to the curve, which can be written as minus c times t times 2 pi over lambda, where c is the speed at which a wave is traveling, t is the elapsed time, so c times t is the displacement, and lambda is a wavelength. This means now that psi of t is equal to a times e to the minus I 2 pi c t over lambda. Incidentally, again, experiments have shown that the Hamiltonian, which is essentially the energy, which we'll call h, is equal to h times c over lambda. Okay, again, as I said, h is Planck's constant, c is the speed of the wavelength, which in this case is the speed of light, and lambda is the wavelength. So c over lambda is the frequency. And using this equation, we can say c over lambda is equal to h, which is a Hamiltonian, over Planck's constant. And so now we can go ahead and write the equation for the wave function, okay, with respect to time, as psi of t is equal to a times e to the minus I 2 pi ct over lambda, okay, or as I said, okay, psi of t is equal to a times e to the minus 2 pi I h t over h, which is equal to a times e to the minus I times the Hamiltonian times t over h bar. This is the wave function for the time. Okay, now for the case now where both the position along the s-axis is moving and the wave function, the curve itself is moving, okay, the angular displacement is going to be 2 pi times s minus c t over lambda. And so now we can say the wave function of s comma t is equal to a times e to the 2 pi I over lambda times s minus c t. And this is basically now translates to psi of s comma t is equal to a times e to the I over h bar p times s minus the Hamiltonian times t. Okay, so now if we take the derivative of this wave function with respect to position, we're going to get partial d over ds times psi of s comma t is equal to I over h bar p psi of s comma t. Okay, now notice that differentiating wave function with respect to position is going to give you a scalar multiple here, okay, of itself. And by definition, this means that the wave function is an eigenfunction of the differential operator with respect to position. Also, this scalar multiple is what we call eigenvalue, okay, this point right here. So now if we multiply both sides by minus IH bar, we're going to get minus I times H bar partial derivative over ds psi of s comma t is equal to p psi of s comma t, or p is equal to minus I h bar partial d by ds. Okay, this is a momentum, okay, as I stated before, and the momentum operator is depicted as a p caret. Now, if we take the derivative of the wave function with respect to time, we're going to get d by dt, and that's partial, psi of s comma t is equal to minus I over h bar times a Hamiltonian times psi of s comma t, or in this case, okay, so we can say now that h times psi s comma t is equal to I h bar partial derivative of psi s comma t over dt. And as you notice, again, the derivative of the wave function with respect to time will give you a scalar multiple of itself. So that's also an eigenfunction. And this here, what we just got here, that's the Hamiltonian. And if we put an h caret, that's essentially the Hamiltonian operator, which again, as I said, acts like energy. Now, because the momentum P is equal to, as I said, P is equal to minus I h bar d by ds. Okay, we can say the kinetic energy now is P squared over 2m. Okay, so P squared over 2m is going to be equal to minus h bar squared over 2m times second partial derivative by ds squared. Okay, if we let the potential energy be, I'll call it PE, equal V sub S, okay, and we will use a caret to depict that that's an operator, just as we can do here for the momentum. We can say then that the Hamiltonian is the potential energy plus the kinetic energy, okay, in which case now we can say now minus h bar squared over 2m second partial derivative d squared over ds squared plus v of s, and that's a potential, is equal to h, and that's the Hamiltonian. And since the Hamiltonian is equal to ih d by dt, that's going to be equal to I h bar d by dt, and that's essentially the time independent Schrodinger equation. Now, if we want the time dependent Schrodinger equation, okay, we'll basically, actually, this is the time dependent Schrodinger equation. If we want the time independent Schrodinger equation, we essentially say that this plus this is equal to h bar, because ih d by dt, that will not be a factor if it's time independent. Okay, now with all this in mind, we're going to change gears a little bit. Okay, and we'll say now that a particle in a bound state, if it's in a bound state, it's going to transition a given position in that bound state more than once. In such a case, if wave functions for the position must be the same every time the particle is in that particular position. For example, if an electron is bound by a proton and separated by a distance of r, so we have an electron here, a proton here, and separated by a distance of r, then the wave function for s, psi of s, must be equal to the wave function of psi of s plus 2 pi r. And that's because they're basically functions of the same. If it's here and it takes a trip around, that's s plus 2 pi r. So it's the same position, which is the same of psi of s plus 4 pi r, or psi of s plus 2n pi r. And that's where n is basically any whole number. Okay, now with that in mind, we can now say now that psi of s is equal to psi of s plus 2 pi r. So now we can write that out and say a times e to the I over h bar p of s minus Hamiltonian times time. And mind you, we don't need this since we're just doing psi of s, but the result will be the same either way, is equal to a times e to the I over h bar p times s plus 2 pi r minus Hamiltonian times t. So what we can do, we can divide both sides by this. So this first side here becomes 1 is equal to e to the I over h bar p times 2 pi r, where e to the I over h bar p 2 pi r is equal to cosine 2 pi p r over h bar plus I sine 2 pi p r over h bar, which is similar to what we talked about here. Okay, so now if that's equal to 1, then basically it can be at 0, or the angular displacement can be 2 pi or 4 pi or 6 pi or 2n pi. Okay, now granted, if it's because of the Heisenberg uncertainty principle, 0 is excluded because an particle cannot have a total momentum of 0. So in this case, now we can say now 2 pi rp over h bar is equal to 2 pi n. Dividing both sides by 2 pi, we're going to get r times p over h bar is equal to n. And so now, if we know that r times p over h bar equals n, okay, we can say now that we can multiply both sides by h bar, and we'll say r times p is equal to h times n, which means now r times p, that's angular momentum, and it means that that's quantized because h bar is a constant and n is an integer. So the angular momentum can be h bar, can be 2h bar, 3h bar, etc. So that number is quantized. Okay, now if we multiply both sides of these by r, we're going to get p is equal to h bar times n over r. And again, this is a linear momentum, and it means that this is also quantized because the values of the linear momentum we can get is h bar over r, 2h bar over r, etc. Okay, um, and now since kinetic energy is equal to p squared over 2m, if p is quantized, that means the kinetic energy must be quantized. We can even go ahead and say r is equal to h bar times n over p, which means that the distance, the radius now, that is also quantized because the radius is going to be h bar over p, or 2h bar over p 3h bar over p, etc. And so now with the R being quantized, then we know that the potential energy is quantized. So if the kinetic energy and potential energy is quantized, it also means that the total energy is quantized. And so with so many values that are quantized, there's no question as to why this branch of physics is called quantum physics. Anyway, that is all I have for now, and I'd like to thank you very much for watching.